We will now continue to use Gauss's law to find the electric field due to extended charge systems. And let's now look at this case. Field due to a uniformly charged sphere. Well, when we left off the last part of this lesson, we calculated the electric field due to a charged shell. Now, this is different. This is not a shell. This is a solid sphere. That is, there is no space in there. There is complete material all over the sphere. Field due to a uniformly charged sphere. Alright, consider a sphere of radius r carrying a uniform volume charge density. See, this time you need to consider charge per unit volume because we are considering the entire volume of the sphere. And so the volume charge density is rho. Well, if rho is the volume charge density, what is the total charge on the sphere? The total charge on the sphere will be rho multiplied by the volume of the sphere. What is the volume of a sphere of radius r? Will be 4/3 pi r cube. Don't forget that. We will be using this as we go on. So, it has a charge density rho, so that the total charge Q on will be Q equal to 4/3 pi r cubed rho. The volume of the sphere multiplied by charge per unit volume. For electric field at any point on the sphere or outside the sphere, this charge Q can be considered to be a point charge. You see, just like the shell, the electric field on the surface of the shell or any point outside of it, the amount of charge on the shell behaves as though it is concentrated at the center. In the same way, for electric field at any point on the sphere or outside the sphere, this charge Q can be considered to be a point charge concentrated at the center. And the electric field anywhere where r greater than the radius is given by what equation? KQ over r squared. And if you replace your K by 1 over 4 pi epsilon naught, it becomes electric field at a distance r where that distance r is greater than the radius. In other words, greater than or equal to at a point on the surface of the sphere or anywhere outside it, the electric field will be ER equal to KQ over r squared, where K is 1 over 4 pi epsilon naught. So this is for the distance r greater than the radius of that sphere. So this is the sphere of radius r. At any point outside or at any point on the sphere, the electric field will be 1 over 4 pi epsilon naught times Q over r squared. Now, to find the field at a point inside the sphere. Now, this time, remember, don't confuse again. The field inside a charged shell is 0. This is not a shell. This is a solid sphere. So, in order to find the electric field at a point inside the sphere, distance r from the center, we construct a Gaussian surface. What kind of a Gaussian surface? The Gaussian surface will be a spherical surface that will enclose a spherical volume inside that surface. So we construct a Gaussian surface of radius r. So this is the sphere. We construct inside that sphere a spherical shell of radius r. and this is the Gaussian surface, and we want to find the electric field at a point on the Gaussian surface. Remember, the Gaussian surface is constructed in such a way that the point where you want to find the electric field is on the Gaussian surface. So we want to find the electric field ER at this point on the Gaussian surface. Alright, that's simple now. You can use Gauss's law very easily. If E sub R is the field at any point on this Gaussian surface, what is the net flux leaving this surface? I'm sure you can now tell me. What is the total flux leaving that Gaussian surface? The Gaussian surface is a sphere. What is the area of that Gaussian surface? Will be 4 pi small r squared. And ER is the electric field, means flux per unit area is E. So if you multiply this E with the area 4 pi r squared, that is a measure of the net flux leaving the Gaussian surface. So phi net equal to 4 pi r squared, which is the area of the Gaussian surface, multiplied by E sub r, which is the electric field at a point on the Gaussian surface. Now, by the total charge inside the sphere, what is the total charge inside the sphere? Inside this sphere, you see the Gaussian surface encloses a sphere of radius r. What is the volume of that sphere? The volume of this sphere is 4/3 pi r cube, where r is that small r. And if you multiply that volume with rho is the volume charge density. So the total charge inside the sphere of radius r is Q inside. What does Q inside mean? The amount of charge inside that Gaussian surface is the amount of charge inside that small sphere of radius r. Will be 4/3 pi r cube, the volume of that sphere, multiplied by rho is the volume charge density. Now, if this is the amount of charge inside, what does Gauss's law say? Gauss's law says that the net flux crossing the Gaussian surface equal to 4 pi k times Q inside. There we are. So, phi net equal to 4 pi k times Q inside, or 1 over epsilon naught times Q inside. Remember, both can be used at any time without any problem. 1 over epsilon naught times Q inside is the same as 4 pi k times Q inside. So 4 pi r squared times ER is the net flux. And that net flux must be equal to the total charge. That will be 1 over epsilon naught times the total charge inside the Gaussian surface. The net flux equal to 1 over epsilon naught times Q inside. And now, let's simplify that. Well, we can calculate or solve for ER from there. After, you can see pi and pi goes, 4 and 4 goes, r squared on the left will go with r cube, leaving an r there. So what will be ER equal to? Can you solve for ER from there? ER equal to rho divided by 3 epsilon naught times that r. Remember, the r squared cancelled with r cube, leaving an r there. Like this. You have a 4 pi on the left cancelled with 4 pi. R squared on the left cancelled with r cube, leaving an r. So ER equal to, you have rho divided by 3 epsilon naught times R, and this is the expression for electric field at any point inside the charged spherical object. That is not a shell, it's a solid sphere. Okay. Now the field inside the sphere varies directly as R. What does that mean? That means inside the sphere, the electric field at the center is 0. When this R is 0, the electric field is 0. And as you move away from the center, the electric field increases. The electric field is the maximum at the surface of the sphere. What is the electric field at the surface? KQ over the square of the radius. And now if you go outside the sphere, the electric field will decrease. Alright, let's draw a graph representing that. The electric field at any point inside the spherical charged object. Now the yellow is the spherical charged object. Any point inside the electric field is rho over 3 epsilon naught times R, and at any point outside it is 1 over 4 pi epsilon naught times Q over R squared. This means that the field increases linearly from the center of the sphere until it reaches the surface. It has a maximum value at the surface where R equal to the radius, and then decreases away from the center where R is greater than the radius. So this is how the electric field varies inside a solid sphere. The electric field increases from 0 to a maximum. Where do you have the maximum electric field? We have the maximum electric field at the surface, and as you go away from the surface, the electric field decreases, becoming 0 eventually. Okay, let's now use this to solve a problem. A sphere of radius 6 centimeter carries a uniform volume charge density 450 nanocoulomb per meter cube. What is the total charge on the sphere? Well, you can do that very easily. Total charge on the sphere will be the volume of the sphere multiplied by the value of the volume charge density. This is rho. Rho multiplied by the volume will give you the total charge on the sphere. Find the electric field at R equal to 2 centimeter, that is inside the sphere. R equal to 5.9 centimeter, again it is inside the spherical object. R equal to 6.1 centimeter outside. R equal to 10 centimeter is again outside. Alright, let's get going. The radius of the sphere is 0.06 meter, 6 centimeter. Rho, the volume charge density, is 450 nanocoulomb per meter cube. Well, this is not written correctly. You must write it nanocoulomb per meter cube. That is the unit of rho. So that will be like this, nanocoulomb per meter cube. There's an M missing in between there. And what else do we know? We know rho, oh well, I just repeated it with the same mistake. The total charge Q is the volume of the sphere multiplied by rho. 4/3 pi R cube. R is the radius of the sphere. So 4/3 pi R cube is the volume multiplied by rho, and the volume is 0.06 meter. And that is 4.07 times 10 to the negative 10 coulomb is the total charge carried by the sphere. We now want to find the electric field at r equal to 2. R equal to 2 is inside the sphere. What is the expression for electric field inside the sphere? E sub r is rho over 3 epsilon naught times r. We know rho, we know epsilon naught, we know r equal to 2 centimeter, that is 0.02 meter. So use all those values there, we get the electric field is 339 Newton per Coulomb. Well, what is the electric field at r equal to 5.9? The same relation. Our r now is 0.059. So replace that r by 0.059. Everything else remains the same. And that field is 1000 Newton per Coulomb. You can see as we move away from the center towards the surface, the electric field increases inside the spherical conductor or the spherical charged object. And now I want to find the electric field at r equal to 6.1 centimeter. That's a point outside the sphere. And the expression for the field outside is 1 over 4 pi epsilon naught q over r squared. This can be replaced by kq over r squared. Alright, let's use this relation anyway. Alright, q, the amount of charge on the sphere, is 4.07 times 10 to the negative 10. 4 pi times epsilon naught times r squared. That is 983.5 Newton per Coulomb is the electric field at r equal to 6.1 centimeter. How about the electric field at r equal to 10 centimeter? Well, the only difference is this distance where? This distance 0.061 we used earlier will now become 10 centimeter or 0.1 meter. There you are, and that value is 366 Newton per Coulomb. Well, problems, once you know the basic method, problem solving in these areas are fairly simple. We will now use Gauss's law to find the electric field at a distance r from an infinitely long charge. Well, this is a long object. An infinitely long charge will extend to both sides. And I want to find the electric field at a distance r from it. And we're going to use Gauss's law. What is the method? Well, the method is every time you want to use Gauss's law to find the electric field at a point, you need to construct a Gaussian surface that contains the point. And the Gaussian surface must enclose some charge from the object that we are using. That means if I want to find the electric field at this point, I must use a Gaussian surface that will be a cylinder that will enclose part of this infinite charge. You see that? So I have to find the electric field at this point. I will take a Gaussian surface that will be a cylinder that will enclose a certain length of the infinite charge. Okay, that's the method. Let's go. Consider an infinitely long charged conductor which has a charge per unit length lambda coulombs per meter. The linear charge density. Now, this is the infinitely long charged conductor. We need to find the electric field at a point distance r from this charge. So what do? By symmetry, the field lines radiate uniformly outward if lambda is positive and inward if lambda is negative. So if this is a positively charged object, the field lines will radiate outward. Is that right? That means the field lines will be crossing this cylinder at right angles in that direction and also downward. All over the spherical surface, the field lines will be radiating outward. If the charge on this is negative, the field lines will be directed inwards. Now we take a Gaussian surface, which is a cylinder enclosing a length L of the charged object. Is that right? And the point where we want to find the electric field is on the surface of the Gaussian surface. It's very important to know that. Now, if R is the radius of this cylinder, you see, the cylinder we constructed has a radius R, means R is the distance of the point where you want to find the electric field. Then what is the surface area of this cylinder? Can you figure out the surface area of the cylinder? Let's take one more look at this. Suppose this is the infinitely long charge and I want to find the electric field at this point, the distance R from it. What do? I construct a Gaussian surface. That will be a cylinder of radius R. Let me see if I can construct that cylinder. Alright, I'm struggling here. Well, here is the cylinder and the charge inside. Alright, what is the surface area of this cylinder? Alright, my charge has fell off. This is the Gaussian surface, right? What is the surface area of this? The surface area will be, if I straighten it out, this will be the surface area, which is given by this length multiplied by this width. But this width, when it is a cylinder, is a circle of radius R. Is that right? Now, that circle has a radius R, so that would be 2 pi R times the length. That is the area. So the area of the Gaussian surface is 2 pi R times the length. This is 2 pi R times the length is the area of the Gaussian surface. Why do we need the area? If E is the electric field at any point on the Gaussian surface, then what is the net flux crossing the Gaussian surface? The net flux crossing the Gaussian surface will be its area multiplied by E. What does E stand for? E stands for flux per unit area. So phi net equal to the area of the Gaussian surface multiplied by flux per unit area, that is the electric field. Well, we now know the net flux. Now, do we know the amount of charge inside the Gaussian surface? Well, inside the Gaussian surface we have a length L of the charged object and the linear charge density is lambda. Therefore, what is the amount of charge carried by that length L? It will be L times lambda. The net charge inside the Gaussian surface of length L is Q inside. That is the amount of charge inside the Gaussian surface is L lambda. Now we know phi net, we know Q inside, we can now use Gauss's law. Phi net equal to 1 over epsilon naught times Q inside, or 4 pi k times Q inside, whichever equation you want to use. Well, phi net equal to 1 over epsilon naught times Q inside. Phi net is 2 pi R LE and Q inside is L times lambda. And now I can now cancel L on either side and solve for E. What is E equal to? E equal to lambda over 2 pi epsilon naught times 1 over R. Now, why I wrote like this? Because lambda over 2 pi epsilon naught is a constant. And that means field at any point varies inversely as the distance from the charge. As you move away from the charge, as the distance r increases, the field decreases. Well, this is the expression for the electric field at a point distance r from an infinitely long charged conductor. All right? Let's now look at charge and field at the surface of a conductor. Charge and field at the surface of a conductor. All right? A very important concept, so listen carefully. A conductor allows free charges to move within itself. Now, this is an aluminum rod, it's a conductor. If I have some free charges inside here, it will allow the free charges to move. Now tell me, what will make a free charge to move? Well, in order to make a free charge to move, you must have an electric field. Only an electric field can produce a force on a charge. So, if I have an electric field inside this conductor, then the free charges inside this conductor will move. Alright. If there is an electric field inside a charged conductor, it will make free charges inside it to move, causing an electric current to flow. Now, is this going to be true? If I place some excess charge on this aluminum rod, will there be electric current flowing in this? Well, I don't think so. Well, what does that mean? If there is no electric current, it means the charges are not flowing. And if the charges are not moving, it means there is no electric field inside the conductor. You see, that's a very simple conclusion. So, this causes redistribution of electric charges in such a way that there is no net electric field inside the conductor. So, if you charge a conducting material, then there will be redistribution of charges occurring in such a way that there is no net field inside a charged conductor. Now remember, in the previous case we talked about a charged sphere. That is not a conducting sphere. It is a non-conducting sphere. We talked about the electric field inside that material. But if it is a conducting sphere, there will be no electric field inside that sphere. The electric field inside a conductor will be zero. Why? Because if the electric field inside a conductor is not zero, then the free charges inside the conductor will be in a state of perpetual motion. You know that a conductor contains free electrons. And when these free electrons are in a state of perpetual motion, there will be a perpetual electric current in that conductor. Well, that would have been fine for us, but that doesn't happen. Therefore, our conclusion is there is no electric field inside a conductor. When this happens, all the free charges will reside on the surface. So, if you give free charges for a conductor, all those free charges will reside on the surface. We can use Gauss's law to show that when there is no net field inside a conductor, the net charge inside the conductor is also 0. You see, if there is no net field inside a conductor, that means there is no net charge. So, if you charge a conductor, if you supply electric charges to a conductor, where will all the free charges will be found? They will all be found on the surface of the conductor. No electric charges will be found inside the conductor. So we can conclude the following about a charged conductor. Very important conclusions. Now this is a charged conducting object. What are the conclusions about a charged conducting object? 1. All the charges on a charged conducting object will reside on its surface. Second, the electric field inside a charged conductor is 0. There will be no electric field inside a charged conductor. 3. The electric field at the surface of the conductor is at right angles to the surface everywhere, irrespective of the shape of the conductor. Now, what does that mean? If you have a conductor like this, that statement says the electric field at any point on the conducting surface will be at right angles. Now, what happens if the electric field is not at right angles? Now, suppose the electric field is like this, not right angles. If the electric field is like this, you know that a vector that is at an angle has a horizontal component and a vertical component. So, if the electric field is like this, there will be a component of the field along the surface. And if there is a component of the field along the surface, that electric field will make these electric charges to move. Again, it will create a current on the surface of the conductor. Since that doesn't happen, we know it doesn't happen. Now, since it doesn't happen, we can conclude that there will be no electric field along the surface of the conductor, which means all the electric field is at right angles everywhere on the surface of the conductor. The electric field at any point on the surface of the conductor will be at right angles, irrespective of the shape of the conductor. So you must be familiar with these properties of charged conductor. Let's do an example. An uncharged metal slab has square faces with 12 centimeter sides. It is placed in an external electric field that is perpendicular to its face. Now, you should know that if there is an electric field in this room, if I place an uncharged metal slab in the electric field, what will happen inside that metal slab? Remember, the electric field will make free charges to move. So inside the metal slab, the electrons will move opposite to the direction of the field. Remember, the direction of the electric field is the direction of motion of a positive charge. That means the electrons will move opposite to that. So if there is a field going like this, now is it from left to right for you? Yes. If there's an electric field that goes from left to right, the electrons in this metal will move from right to left. They will all get accumulated on this face, leaving the other face positively charged. So the net effect of placing this metal slab at right angles to an electric field is one phase of it will get negatively charged and the other phase will get positively charged. We call it the induced charge. You see, each phase will get induced electric charge. Alright, the total charge induced on one of the faces is 1.2 nanocoulomb. Now you understand what's the meaning of the induced charge. What is the magnitude of the electric field? What is the magnitude of the electric field in which that metal slab is placed? Okay, now here is the metal slab and this is the electric field. One face of the metal slab gets induced negative charge and the other face gets induced positive charge. The surface charge density on the metal slab sigma is Q over A, is that right? If Q is the total induced charge, then the surface charge density will be Q over the area. What is the area of one side of the slab? It is of side 12 centimeter. Area is 0.12 multiplied by 0.12. So Q, the induced charge, we are given the induced charge. The total induced charge on one of the faces is 1.2 nanocoulomb. So that Q is 1.2 nanocoulomb. That is 1.2 times 10 to the negative 9 coulomb. And the area is 12 centimeter times 12 centimeter, 0.12 meters squared. That will be 8.33 times 10 to the negative 8 coulomb per meter squared. And that is the surface charge density. Now, the field outside a charged conductor is En equal to sigma over epsilon naught. Well, if you don't remember this, you need to remember this. The electric field outside a charged conductor is sigma over epsilon naught. And sigma we just calculated, epsilon naught we know. Therefore, that will be 9,416 Newton per coulomb is the intensity of that electric field. Alright, let's do another one. If the magnitude of electric field in air is as great as 3 times 10 to the 6 Newton per coulomb, the air becomes ionized and it begins to conduct electricity. Now, how many of you have experienced when you go and try to open the car, you get a shock? Now, why is it happen? Why does it happen? You see, during the dry season, when your hands rub against your clothes, especially if it is polyester, you accumulate a large amount of charge on your body. And when you try to open the car, these charges will jump from your body to the car. In other words, the air becomes conducting. If I place a large amount of charge on this metal sphere, soon it will start sparking. Now, what is the process of sparking? It will make air around it a conductor. You see, the air becomes conducting and electric charges will begin to move through that air. And how much electric charge, or what should be the electric field? What is the maximum electric field in order for that to happen? If I can place enough charge on this so that the electric field on the surface of this conductor is as great as 3 times 10 to the 6 Newton per coulomb, then there will be dielectric breakdown. Now, what is the meaning of dielectric breakdown? You see, a dielectric is an insulator, something that does not allow electric charges to move through. What is the meaning of dielectric breakdown? That property is broken down. Broken down under what conditions? When the electric field is very high. So a very high electric field can break down the insulating property of air and make the air conducting. and that happens at this very high voltage. So that must be clear as we do this problem. If the magnitude of the electric field is as great as 3 times 10 to the 6 Newton per Coulomb, the air becomes ionized. What's the meaning of ionization? Air become ionized means the atoms of air gets ripped apart. You know, an atom as a whole is neutral. If it gets ripped apart, then it produces a positive part and a negative part. They are called ions, and they are free charges. Now, when air contains free electric charges, it becomes a conductor. You see, it can now allow electric charges to flow through. Now, this high electric field will produce ionization, which results in the dielectric breakdown. Okay, a charge of 18 microcoulomb is to be placed on a conducting sphere. What is the minimum radius of a sphere that can hold this charge without producing dielectric breakdown? Now tell me, what is the electric field on the surface of a charged sphere? We have talked about it several times. What is the electric field on the surface of a charged sphere? It will be kq over r squared. So q, the amount of charge on the sphere, is 18 times 10 to the negative 6. 18 microcoulomb is this many coulombs. We need to find the value of the radius r of that sphere, which will produce a maximum electric field. In other words, the electric field will not exceed this value. If the electric field exceeds this value, it will create dielectric breakdown. Now, in order to prevent the dielectric breakdown, we need to keep the electric field within this range. So we will go up to this value. So we say electric field is 3 times 10 to the 6 Newton per Coulomb. If r is the radius of the sphere, then sigma equal to q over 4 pi r squared. If q is the total charge on the sphere, then the area of the sphere will be 4 pi r squared. The total charge divided by the total area will be the surface charge density. Now, q is 18 times 10 to the negative 6 divided by 4 pi r squared, and that will be the surface charge density. And what is the expression for electric field just outside a conductor? I simplified this and I wrote it as 1.43 times 10 to the 6 divided by r squared. In fact, 18 divided by 4 pi, is that correct? Take a look. So sigma equal to 1.43 times 10 to the negative 6 over r squared, where this 1.43 is 18 divided by 4 pi. Now, the electric field En just outside the conducting sphere is sigma over epsilon naught, which is actually kq over r squared. It will give you the same result. So E equal to sigma over epsilon naught, and sigma is this value. So if you now replace sigma by this value and use epsilon naught is 8.85 times 10 to the negative 12. This will be the electric field. And what is the maximum possible value of this? 3 times 10 to the 6. This quantity cannot be greater than 3 times 10 to the 6 Newton per Coulomb. So we take this quantity and set it equal to 3 times 10 to the 6th, and then solve for r. That's a very simple equation. We can solve r squared equal to this quantity divided by this number times this number. and that will be 0.055 or R equal to 0.235 meter. Okay, that's been a good problem. Well, we have used Gauss's law effectively in obtaining electric fields due to extended charged objects, and also we discussed about the properties of a charged conductor. Alright, I want you to keep this information so that we can use them in our next lesson. We will discuss a new concept in the next lesson called electric potential. Alright, I'll see you for that lesson in a little while.